Hello everyone. In this talk, we'll discuss about basics of crystal structure. The, the solids are generally classified on the basis of arrangement of its constituents, and there are mainly two types. In one, which is called the crystalline solids, the constituents, if I consider the constituents are atom, they are perfectly and periodically arranged over large distances. You can see that here all the points are regularly arranged and periodically arranged. These type of solids are called crystalline solids, and in another, the constituents are distributed or arranged randomly. This type of solids are called amorphous solids. Let's see the basic difference between one crystalline solids and amorphous solid. Constituents are arranged perfectly and periodically over long range in a crystalline solid, and in an amorphous solids the constituents are not arranged periodically, which we have seen in the last figure. Now generally the crystalline solids are anisotropic, amorphous solids are isotropic. The crystalline solid possesses a soft melting point and begin to melt at a specific temperature. They have a specific melting point, which is not the case for amorphous solids, and they soften gradually over a temperature range and can be shaped into various shapes when heated. You can consider like one plastic. So if you heat a plastic, it will not melt, but it will change its shape. It will get softened. This So plastic is one example of amorphous solid. So crystalline solids are true solids, whereas amorphous solids they are pseudo solids. Example of crystalline solid: salt, NaCl, zinc sulfide, diamond, etc. Amorphous solid: plastic, rubber, glass, etc. Now, the solids can be classified onto another type, which is called single crystal and polycrystal. So, in single crystal, the constituents are arranged periodically and regularly over the entire volume. You can observe that the periodicity is constant over this large volume or over the entire volume. These type of solids are called single crystal, where the periodicity across the whole volume. The periodicity occurs across the whole volume. In another case, if the periodicity occurs only over small regions or small volumes, or called grains. So if the constituents are arranged over small volume or grains, then these type of solids are called polycrystals. So here you have periodicity, you have regularity of the constituents. However, they are not arranged regularly or periodically over the entire volume, but over small regions. These type of solids are called polycrystal, and amorphous solids, which we have already discussed, they are not periodic at all. The constituents are arranged very randomly. Now, one important point is that any physical property is most prominent in single crystal of the material. So, in single crystal, the property is most prominent than polycrystal or amorphous solid. So, for example, let us discuss about this. So, this is resistivity as a function of temperature. For this set of measurement has been performed in single crystal of this sample, which is called ER2 IR3 Si5, and this data is performed on the polycrystal of the same material. So there is a distinct difference. There's a distinct difference. One is this: here so there is a sharp transition in resistivity around 150K. If I so this is for the cooling data. So if I cool, so there is a there is a sharp increase in resistance or resistivity around 150K for the single crystal. However, if I go to polycrystal around 150K, there is a small change in resistivity, no transition, no sharp transition, just a continuous change. So, so in these two data, you can see that this transition, this transition in resistivity is most prominent for one single crystalline material than one polycrystalline material. So, as I discussed, any physical property is most prominent in single crystal of the material, and that's why in the field of research, the single crystals are so important in understanding the fundamental properties of materials. Now, let's go back to single crystal. Generally the single crystals are formed of two things. One is lattice and another thing is basis. Lattice and basis. We'll discuss this lattice and basis. What do they mean? Suppose I have a set of geometrical points. So these are a set of geometrical points which are arranged in space in very regular and periodic way. Now if I consider any of these points, suppose I consider this point. So it has one surrounding or neighbor. So if I consider the neighbor of this atom or surrounding of this atom which is almost identical to this. So the surrounding for this atom and this point and this point or this point are almost identical. Such arrangements of atom in or points, I should say point instead of atoms, such arrangement of geometrical points in space so that the surrounding or the crystal looked almost the similar when I view it from one point to the another, then such arrangement of points are called crystal lattice. Such arrangement of points are called lattice or crystal lattice. So if I see a cross-sectional view or 2D view, I should look like this, where these are all these mathematical or geometrical points. So if the geometrical points are arranged in such a way that when the lattice is looked from one point, it looks the same when it is looked from the or it is viewed from the another point, then such arrangement of geometrical points are called crystal lattice. So it's a mathematical the concept of lattice is a mathematical concept. It's a regular periodic arrangement of infinite array of geometrical points which looks identical when viewed from any point r prime of the array which I discussed. So suppose this point is r prime and this is r, so they look almost the similar, identical. So looks identical when viewed from any point r prime of the array to any point r, where r prime and r are connected to with this equation. N1, N2, N3 are the integer. I'll come to this. And a1, a2, a3 are called translation vectors, or the primitive translation vectors are also called a primitive lattice vector. I'll come to this. Now, this crystal lattice or lattice, simple lattice, it satisfies certain symmetry operation which is beyond this discussion. Now, let us discuss the concept of unit cell. Suppose this is a two-dimensional arrangement of geometrical points or a 2D lattice. Now, in this 2D lattice, let us consider this small space. This is a small space. Now what will happen if I translate if I repeat this space? So if I translate this in this direction or repeat this space in this direction, I can actually span the lattice, or I can feel the entire space of the lattice. So you see, so I am repeating this one. So if I repeat in this way, I can actually feel all the space. So an unit cell is a space. So this small space is called one unit cell. So an unit cell is generally it's a smallest volume. So it's a space of the lattice repeating or translating which the whole lattice can be spanned. So if I repeat or translate this small space, I can actually span the whole lattice. So this small space is called one unit cell. Now its choice is not unique. Why I have said this? Because let's us consider this small region. So again, if I repeat this, I can feel the entire space. So suppose I have this. Right, here also, if I repeat this structure, I can feel all the space. So this is a choice of unit cell. This is also another unit cell. So its choice is not unique. Even I can choose this third region which looks like this. So this is also one unit cell, because if I repeat this, I can feel the entire space. But this is not the smallest area or the smallest volume. Now, if the unit cell contains only one lattice point, it is called primitive unit cell. What does it mean? For example, suppose I consider this point. Now, this point is shared by this unit cell. If I consider one unit cell here, this is shared by this one also. This is shared by this unit cell also. This is shared by this unit cell also. So, in this 2D structure, around this atom or this point, I have 4 unit cell. So, each of these points is shared by 4 unit cell. So 1/4 of this corresponds to this unit cell. So 1/4 of this corresponds to this unit cell. And how many points this unit cell has? 1, 2, 3, 4. 4. So 4 into 1 by 4 is equal to 1. So this unit cell has only one lattice point. Such a unit cell is called a primitive unit cell. Similarly, this is also one primitive cell. You can go back and you can check. This is also one primitive cell. Now, if I come to this, each of these corner points are shared by 4. So 4 into 1 by 4. So these 4 points corresponds to one unit cell, one lattice point. However, I have these 2 points also, and this point in this 2D lattice is shared by 2 unit cell. One is this, another is this, and this one also is shared by 2 unit cell. One is this, another in this side. So 2 into 1 by 2 is equal to 1. So so 2 into 1 by 2 is equal to 1. So 1 from the corner points, 1 from this point. So I have 2 lattice point in this unit cell. So this unit cell has 2 lattice points. So this unit cell is not a primitive unit cell. It is called one non-primitive unit cell. So unit cell 1 and 2 are primitive unit cell, and this 3 is a non-primitive unit cell. Now let us consider this space. Now I can mathematically define this space by two vectors. One is this a1 is equal to a1x, and another one is this one a2 equal to a2y. Now if I have one square lattice, I should have a1 is equal to a2, but generally I am taking that a1 is not equal to a2. So a1, so I'm considering this is at x axis, this is y axis. So a1 equal to a1 x cap, a2 equal to a2 y cap. This vector a1 and a2, they span the lattice, or they can fill the entire lattice space by translation. So if I just translate this vector, so it can fill all the space the way we have done it in the previous slide. So, for example, like R1 is equal to say N1 A1, R2 equal to N2 A2. So, for this one, I have N1 equal to N2. Now, so if I have N1 equal to 2 and N2 equal to 1, so I have N2 N1. So I can fill this amount of space. If I have N1 equal to 2, N2 equal to 2, I can fill this amount of space and so on. So primitive lattice vector by translation can fill the entire space, and this primitive lattice vector, they actually define the unit cell or the lattice. Now, this choice of units, choice of primitive lattice vector depends on the choice of unit cell. For example, for this one, I have a1 is equal to a1 x cap, a2 equal to a2 y cap. However, for this, my a1 is a1 x cap, but you can see a2, this is a2 and a2 equal to a1 plus this is a2 y cap. So a2 is equal to a1 plus a2 y cap. So then vector a1 and a2 are called the primitive lattice vector. So if the a1 and a2 is defining one primitive unit cell, then these vectors are called primitive lattice vector. For 3D, we'll have three vectors to define one unit cell: a1, a2, and a3. In a lattice, all the points can be defined by the vector r is equal to n1 a1 plus n2 a2 plus n3 a3. I'll come to this for a 3D lattice. So let us consider this 2D lattice. For a 2D lattice, as I said, all the lattice point can be defined by this r. For example, to define or to represent this point O, which is at the origin, say I can set n1 equal to 0 and n2 equal to 0. Now, for example, if I consider this point A, for point A, I should have to define this A with this, to represent A with this R vector, I should have n1 equal to 1 and n2 equal to 0. Similarly, if I consider the point B, I can represent this point B by considering n1 equal to 0 and n2 equal to 1. Similarly, if I consider the point C, for point C, I should have a 1, 2. So n1 should be 2 and n2 should be 0. For point D, similarly, I should have n1 equal to 3 and n2 equal to 0. For point E, I should have one step and one step in this direction. So n1 equal to 1 and n2 equal to 1. Similarly, point F, n1 equal to 2 and n2 equal to 1. Point Z, n1 equal to 1, n2 equal to 1, 2. So in this way, you can see that we can represent all the points by this simple R vector, which is actually represented by this primitive unit cell. Now for one 3D lattice, I should have N1 A1, N2 A2 and plus N3 A3. So for one primitive this unit cell, so what is the area of this two-dimensional unit cell? It's A1 cross A2 and the direction is out of the page. Similarly, for a 3D lattice, the volume is A1 dot A2 cross A3. So now let's move to basis. What do you mean by a basis? So in lattice, we have seen that it's an arrangement of geometrical points. However, one crystal is actually it is made of atoms, molecules, and lattice is one mathematical concept. So to fill the single crystal with atoms and molecules, I have to put now or add atoms or molecules at all those geometrical points of a lattice. So that is actually basis. So what is the basis is? A single crystal is formed when we add atom or ion or a group of atoms or ions to each and every points of the lattice. These constituents are called bases. So this atom, ion, or the group of atoms are called bases. So basis plus lattice is equal to one crystal, a single crystal. So I have one lattice, and let us consider one small atom. Now, if I add this atom at each of these lattice point, I can fill such one crystal. So although this lattice is consists of only geometrical point, this is actually made up of real atoms or molecules. So every basis in a given crystal should have, so this is one important point, that every basis in a given crystal should have identical arrangement, composition and orientation. What does it mean? Let us consider this another one. So I have this lattice and I have this basis. Now, as I said, that they should have identical arrangement, composition and orientation. So if I add these two atoms in the similar arrangement, composition and orientation, it should remain like this at each of these lattice point, then I can form this crystal. So say this. Now, although the lattice was so simple, because of this choice of this basis, this kind of basis, I have such a complicated crystal. But now, if I can identify my basis from this type of complex crystal, I can go back to a simple lattice. And if I know the lattice and I can identify one unit cell, then the description of the crystal is so simple. By just describing this unit cell and the basis, I can actually study such a complicated crystal. So that's why the concept of lattice and basis is so important. Now let us consider now what do you mean by lattice parameter? Lattice parameter are the set of parameters which specify the unit cell. So suppose I have this unit cell. Till now I have explained that the unit cell can be represented by the vectors a1, a2. But if I have a three-dimensional space and I want to know the lattice parameter, or I want to identify or represent this three-dimensional space, what I want, I need these three vectors a1, a, b and c. Further, I need also the angle between them. So lattice parameter means these six things. One is these three vectors and and these three angles between them. They actually in this way I can completely define one unit cell. So the lattice parameter, the set of parameter means three vectors and three angles which specify the unit cell. For example, here the lattice parameters are A, B, C and the angles alpha, beta and gamma. So for one simple cubic structure, so if I consider this simple cubic structure, so in this, so simple cubic structure means all the sides are equal. So for this unit cell, I have all the sides equal and all the angles 90 degree. So A1, A2, A3. So all the sides A1, A2, A3. The magnitude of A1, A2, A3 must be equal, and this value of this angle are all pi by 2. So and if the sides are a, I can represent a1 equal to ax cap, a2 equal to ay cap, a3 equal to az cap and alpha, beta, gamma are pi by 2. So these are the set of lattice parameter which represent one unit cell of a simple cubic structure in 3D. Thank you for now. So we'll meet in the next video.